Our final speaker is Christian Copetti from Oxford, who will tell us about categorical symmetries and 1+1 dimensional scattering amplitudes.
Okay, so I'm going to also thank the organizer for inviting me here. I'm a bit of an outsider of this community, so it's nice that things open up a bit. And I try to keep the talk a bit short so we can go to lunch in time, I guess. So I'm going to talk about how symmetries can enter in scattering amplitudes. It's based on a letter I wrote with my collaborators Lucia Cordova and Shota Komatsu in March and some upcoming work. So let's just situate the talk a bit. Like one part will be generalized symmetries, which is not this conference, but I will try to give some background so it's understandable. Another part is scattering amplitudes. And we will just work in 1+1d, so we will use integrable examples. So this part is integrability in this sense, and this is my talk. And the aim is to discuss how generalized symmetries, which I will introduce, can act on S matrices, and how they can give physical consequences in scattering. Okay, and this will not be symmetries that you see in the Lagrangian of the theory. So there will be some kind of more maybe mysterious stuff, but you can still describe their action. And we will correct some ancient kind of small mistakes. So the summary of the talk, so that's good to give in advance. So we will show how this generalized symmetry act on massive kinks. So the setup will be always scattering of massive kinks between like discrete vacua, and how they lead to word identities for the 2-to-2 S matrices. You can do other cases, but this will be like the setup. And this is just a representation. This red line is always a symmetry generator for me, so this will be the notation. And then we'll show that if we impose symmetry, which is this equation, and unitarity of this matrix, and also the Yang-Baxter equation. The Yang-Baxter equation is not like important, but it's there in the examples. Then this is incompatible with crossing symmetry. So like the fact that the S matrix is symmetric is like a principle of nature that is more important than crossing. And then crossing is slightly modified in the following manner. And I will introduce what the factors are, but you see there is some prefactor here, which is non-trivial. And to conclude, I will also mention how you can input this data of these categorical symmetries in S-metric bootstrap. It's quite doable, and how you can get some nice constraints and matches with the literature. But Lucia will talk about this in the lecture, so I will just flash one slide. Okay, so philosophy. So many times in integrability, people kind of do the opposite of what I think about in quantum field theory. So you like start from the IR and you kind of reconstruct things in the UV. So like the idea of the talk is that we start from the deep IR, we just have some vacua, that's discrete, and there will be some symmetry that swaps them, okay? And the proper name is that these are symmetric TQFT, but it's just a discrete vacua. And if you go up in scale, there is the scale of the mass of the kinks, and then you have massive kinks which interpolate. Okay, and if you go up all the way, you go to CFT, and then the way you go down is that you deform the CFT by a relevant operator. And what I want to point out is that the symmetry of the problem, which in my talk is going to be this curly C, is always present. So it acts on the vacua there in the far IR. It will act on the kink, which will be the topic of the talk. And you can see it as the symmetry which is preserved by the relevant deformation. The CFT has much more symmetry, but some will be preserved all along the LG flow. This is kind of the setup. Okay. So let me give you just one slide about the categorical symmetry, or generalized symmetries in 1+1 dimensions. So like I will give an example afterwards, but so you should think of this as the set of topological lines of your 1+1 dimensional theory. I think they were discussed first in CFT setup by Petkova and Zuber, and then put in more general footing in these papers, but there's like a huge literature, different point of view, so it's like not a complete list of citations. It's just the fact that they have topological lines. They have some nice fusion structure because they're topological, so if you just go very far, they look like one line. And it's just this equation. Well, these n are integer coefficients. And usually you study a group. For a group, this n is like a delta function, which imposes the group law. No? But you can have more general structures. And some, okay, then some topological junctions will appear, which is just the right way to say that two lines fuse. and there will be some vector spaces there. Junctions are like vector spaces, and the dimension of the vector space is this big N. And there is some constraint with the associativity of this product, which has been discussed for a long time, which boils to the pentagon equation for these F symbols, but this will not be important for the talk, so you don't need to think about it. But one quantity we will show up is the quantum dimension, which is just the wave of the line on a circle. There's a positive number, which is bigger than 1, and they will appear in some formulas. Okay? This is just kind of what you should think about. So let me give you an example, which is the Ising symmetry, which is the simplest one. So you can consider 1+1 dimensional Ising theory, one of the simplest theory. This is the phase diagram as function of the temperature. So at high temperature is disordered, you have one vacuum. At low temperature is ordered, you have two vacua. And there is a well-known duality, which is Clemens-Wannier duality, which exchanges high and low temperature. So it exchanges these two pictures. Okay, let's keep this in mind because it will come afterwards. And at the critical point, this will become a symmetry. It's called the Ising symmetry. So let me just flesh out how it's done. So there is this N defect, which is the Clemens-Wannier duality, which is now something that really acts on the theory. Eta is just a Z2 symmetry, which is equals to 1. And then N squared is 1 plus eta. So it has this weird fusion rule, which is not that of a group. So people say it's non-invertible. And you can compute the quantum dimension from the fusion rules. The one of eta is 1, and the other one is 2. This will be like the coding example, so it's easier to follow. Then we have to start for the first step of the program, which is how symmetry acts on TQFT, no? So it's quite easy to describe 1+1 dimensional symmetric TQFT as a set of boundary conditions. Every boundary condition is just a vacuum of the theory, okay? Because of 1+1 dimension. And the symmetry acts by just ending on the boundary condition and changing it. So it describes some topological junctions. So this is something that you have to give. And they have also some associativity property, like the F symbols. There are some boundary F symbols which qualify. And okay, there's also a way to fuse with the boundary. It's similar to the fusion rule of two lines. You get some other integer coefficients, which denote small n. And they also satisfy a nice algebra, which imposes associativity. And in maths, this is the structure of a modular category over C. So there is some modular category. So there is some mathematical structure which is well studied, which describes this C-symmetric TQFT. But you should think about it's the way in which the symmetry acts on the vector, essentially. Just that will be a bit more abstract in some cases. Now, I give you one example, which is the Ising TQFT. So it's a TQFT with Ising symmetry, is actually the only one. So as you know, the TQFTs with Z2 symmetries are very simple. There are two. There is either the one in which the symmetry is broken or it's unbroken. So you have either one vacuum, which is 0, or two vacua, which are denoted as plus and minus 1. And the Clemens-Wannier transformation exchanges these two things, no? But in a Z2 symmetric way. So you kind of play around a bit and you find the only way that the line can act on this vacua is the following. This is the only Z2 symmetric one, which exchanges the two sets. And if you try to solve the equations for a smaller number, you find no solution. So this is like the only representation. And this will come out in the LG flows afterwards. So keep in mind these three vacua. But this is some kind of thing that always happens. This is called the regular representation. It's just a way in which you can always realize a symmetry. It's like the adjoint representation for Lie algebra. So you just identify the set of vacua with the set of lines. You say there is a special one, which you call 1, and all the other one are obtained by fusions of lines with those. So this is the picture that you should keep in mind. There's like this 1, which is trivial, and then you fuse lines, and then you can just lift them into the bulk, and then you can compute everything. And physically, this describes a complete spontaneous symmetry breaking of the symmetry. So when this happens, it's like you break all the symmetries, and it's particularly simple to describe the kinks. Okay, so this is the first part of the program. This is the first part, which is symmetry action on the IA. Now we go to the, okay, this is also the dictionary for the Ising symmetry. So 0 is just the n line, and plus and minus are 1 and it. And you can see that it's consistent with this dictionary. So this is kind of the main part of the talk, which are the kink multiplets. So we'll try to explain how symmetry can act on the space of kinks. And to do this, is useful to introduce an Hilbert space where kinks are the states. So to do this, I follow this paper of recent paper of Clay and collaborators. So you just go on the strip. So Hilbert space on the interval. Interval is very, very large, much larger than 1 over the mass of the kink. So you are really in the far infrared of the theory. And on the two sides, you put boundary conditions, which are those of the TQFT. So the theory is like in the vacuum at the two boundaries. And then a particle which interpolates between the two sides is a kink that goes from minus infinity from one vacuum to the other. So if you go to energies which are the order of the mass of the kink, the states will be the kinks in this Hilbert space. And the symmetry acts very natural here. You just take a line, you stretch it between the two boundaries, and then you push it downwards. That's how symmetry acts on the kinks. And you can derive an algebra for this action. As you usually do, you take two lines, and then you just resolve it in two ways. So either you, on the right-hand side, we kind of bring them down one after the other. And on the left-hand side, we just put them together, and then we bring one line down. And you get this algebra, which is not very illuminating, but it's a bit of a generalization of a group composition. And this L with the square bracket is just what you should think of the representation of a group. Okay? So given the algebra, you need to find the irreducible representations, which are the multiplets. And I will not tell you like how you do it because it's a bit technical, but there is another set of topological lines, which I call C-dual of M, which labels the irreducible representations. And it's nice to represent them as some lines stretching into the gray side of the picture, which I don't think it shows very well on the line. Okay, but this is just an imaginary space in which the representation theory lives. Okay, if you want to be very conservative, and the endpoint is the kink. So this is a kink in the representation V, and the simplest one is the case in which you study this regular representation, which will be all the examples. And in this case, it's just a normal symmetry. So you can think of every line is a representation also. And the idea is that if you look in the UV, in the CFT, you have twisted sectors for the symmetry. There are some operators there. And if you follow them in the IR, they will become kink creation operators. If some of the symmetry is preserved, the dictionary doesn't work because some of these lines will become transparent in the IR, so you cannot really use it, but for this is kind of a nice intuition. And what is nice about representation theory is that now you can fuse lines on the other side and find the tensor product of representations. This you get essentially for free if you know this dual, this C star M. So it's quite easy to do, and if you have the regular representation, it's completely free. And this describes kink bound states. So this will be useful in the end, in the last slide, to put some coefficients in the S matrix to Z. Okay, so I will give one example, which is always the same. So there is one well-known LG flow. This has been studied by Zamolodchikov in the late 80s, and there are many generalizations in which you start from the tricritical Ising CFT, which is the second minimal model, and you deform by the phi-1,3 field. Is one relevant field. You have to choose the sign in the right way. So I put the minus in my convention, it's convention dependent. And this preserves an Ising symmetry. This is easy to show. So this is kind of what is C along the flow. And it flows to 3 aqua, which is the only possibility. And this was known to Zamolodchikov. You can write down what is the kink representation. It's just the N line. You can ask me later if you want. I can explain why it's this N line. And then there is a known S matrix for this for the scattering of kinks in the IR. This also been written down by various authors, which has the following form. So A, B, C, D now label the vacua, so it's plus or minus or 0. Okay. This is like there is a CD factor, this Z, which is crossing symmetric. There is this vacuum dependent part, which you see is not really crossing symmetric. It has some field factor in front. So to restore crossing, you input something more, which is this green factor, which depends, it's just a phase, depends on if the real rapidity. And you can show that if you don't impose symmetry, you can change the basis in the space of one particle states and put this phase. So it's like something allowed. But if you impose symmetry, it's not allowed. So this I will explain later, but you should think of it this way. But if you don't have the green factor, you have instead this equation for crossing symmetry. And I will show you that is the right equation. So this is the equation which is consistent with the Ising symmetry of the kinks, while the crossing symmetric one is inconsistent. And this is like a general lesson. This is just the example. So to do this, just let me tell you how you derive world identities for the S matrix in a schematic way. So the idea we had was you try to construct the S matrix by starting with a large disk in Euclidean signature with boundary changing operators, which is this one. And you do the right Lorentzian continuation. And you get an S matrix. So the way you do it is you slice time in kind of this way. And then you get, and you take the disk very large. There are some formulas, but I didn't put in the slide. But the nice thing of the disk is that you can really, it's easy to discuss the action of the symmetry. So the symmetry action is just putting a line in the middle if you want. And I can deform it up, I can deform it down, and I can equate it to things. So I get this equation. It's not particularly illuminating, but as you see, you get two S matrices on the two sides, and this LV are just the representation of the symmetry. So this is some constraint that the S matrix has to satisfy. So if I give you an S matrix, I tell you it's Ising symmetric, you have to input these and check. So for example, for the N line, you get some constraints like this. And you can take the ones of Zamologikov and check that if you put the green factor, they don't satisfy this identity. So it's easy to check. And there is a general way to satisfy this identity by just using these blue lines in the right way. So this can be inputted in an easy way. And so now we will just give a derivation of this modified crossing equation, which is constructive. It's a bit more different. So we'll assume that on the disk, the 4-point function is crossing invariant, which I think is a kind of well-accepted statement. So I think we'll assume it. And then we introduce in and out states, which schematically are these things. And the important point is if you compute the norm of this in the file IR, so in the TQFT limit, it's not 1, it's this number. So when you want to compute the S matrix, you have to normalize the states so they have unit norm. That's like the prescription. So you just divide by the square root of the norms in the disk 4-point function. And you get this modified crossing equation. So you see that these are just the norm of the states that are not 1. And then you evaluate it, and you get the formula that you want. And you can do it in more general cases. This is just a simple case. This is a way to show that this is the right prescription. And then if you look at the possible change of basis that you can do, which are rapidity dependent and respect these world identities, you find that you cannot remove this. So it's a small computation, but it can be done. So this is like a physical observable. Okay, so I have like a lot of time left, no? Okay, good. So, and this is just the last slide. So I want to show a bit what you can do with the bootstrap. And then Lucia will tell more about this, I think. So it's the usual S matrix bootstrap approach. So you impose various properties of the S matrix and you try to bound the possible partial amplitudes. And what is not maybe usual is that you impose this modified crossing relation instead and impose symmetry. So this is the kind of important thing. So the S matrix is symmetric from the get-go, and then you try to look at the kind of partial wave expansion of this. So this is the example for Fibonacci symmetry. This is the plot. I will tell you what things are. So here the symmetry is the Fibonacci, which is one of the simplest one. You have just two objects, one W, and W squared is 1 plus W. And this A0 and A1 are just if you take two W particles, they become either 1 or W. So these are the two amplitudes. And there's a special point there, which is there is one coupling, which is G squared, which is just the kink anti-kink into the breather. And there is a special point, which is this fat dot, which corresponds to an integral theory. This was discussed long ago by Smirnov. So it's another deformation of the critical Ising, and that's good, we match it. But there is another special point, which is not shown in the plot, which is on the very bottom at g equals 0, the same corner. And this corresponds to the formation of pots of the D-type minimal models. It's called S in some papers. And so the important point is why is g equals 0? So what is fixing it to be 0? And you can use symmetry arguments to pinpoint the fact. So if you go to this pots theory and you do this deformation, the symmetry is a bit bigger than Fibonacci. So there is a Z2 symmetry more. And so you have four lines. There's a W prime, which is just W times the Z2 symmetry. And you can show that the kink is in W prime multiplet. So for just the Fibonacci symmetry, you cannot distinguish the two. But if you add the Z2, there are two different multiplets. One is charged and one is not charged under Z2. But now from the fusion rules, which is W prime squared is 1 plus W, you see that if you fuse to a kink and an anti-kink, you don't get a breather, right? Because if you fuse to W prime, you cannot get another W prime particle. You must get. So this channel is forbidden by symmetry, and you have to put G equals 0. And indeed, it's the thing that you get in the kind of bootstrap approach. So this is kind of power of symmetry result. But you can do other things. So this is like just a small example. And yeah, so let me just tell you something about future prospects, and then you can ask me more. So there are many things to do, and yeah, I think I'm the main and the main abstraction in this. So I should dedicate more time to this. So one thing is to understand which physical observables are modified by this crossing equation. So it's known that if you do like TBA for the untwisted sector, you compute a central charge, it doesn't matter because this was done in the 80s. But what is promising is instead do the TBA for twisted sector observables. So you look at the Hilbert space on the cylinder with the line going this way. And you can show that the world identities for the S matrix are needed to preserve integrability. So this is a nice simple thing to show. And now we know how to do this a bit, so we can kind of attack the problem. And we hope that here these factors will be important in determining this data. Another nice thing is that you can try to now input the symmetry in the IR and try to reconstruct some UV-CFTs you don't know. And there is one kind of relevant case in some of the literature, which is called the Agerup symmetry. It's some weird symmetry category which has 6 lines. And people wanted to show that essentially every symmetry can be realized in a CFT. And this has been realized on the lattice, but there is some error bars in the quantities. So one could try to write down a symmetric S matrix for a possible interval description and go up and see what are the data there. This is something that we're thinking about a bit. It's not very easy to do, but it's nice if it works. Then perhaps the most exciting thing is to do higher dimensional examples. This is just 1 plus 1D. You can do many things, but it's all well studied. So there are some results in 3D by Minwalla and collaborators about modifications of crossing symmetry for Chern-Simons matter theories. So it would be nice to make them more kind of concise and put them in a general framework. And then there is also the problem of scattering of fermions on monopoles in 4D, which is infamous, for example, with the Kalan-Rubakov effect. And recently people have argued that you can use generalized symmetries to explain what is the state of the outgoing particles. But it would be nice to see if something might be said by also using crossing symmetry. And yeah, last point is a more like technical one, which I like, but is the relationship between this modified crossing and Toft anomalies. So maybe all this, the example that I showed you, the theory has various vacua because the symmetry is anomalous. So by anomaly matching, you cannot have a symmetry preserving phase, which is gapped. But it would be nice to show that this modified relation relies on the fact that you have a Toft anomaly, so like the other way around, but we don't know yet. It's for future work. Okay, and I'm done.
Thanks. I think we can take a few questions now.
Hi, just one naive question. So when you do the S matrix bootstrap, use this modified crossing. How do you modify the row alias in the bootstrap?
The what? Sorry.
The alias. I assume you're using the S matrix bootstrap by making some alias of the S matrix and require the unitarity, right? Or it's a different things.
Well, essentially, it's slightly different because what we use a kind of peculiar basis which imposes symmetry from the get-go. So it's not like the usual one in this sense.
I see.
But yeah, I couldn't really introduce the details. But it's what you expect, like when you just decompose everything in the tensor product representations, but you need to use the right ones.
I see.
And then you can write in that basis all the various equations in a simple way by some linear equations. So then it goes the usual way. But this step I didn't present. But I think when we write the paper, it will be there. So it's that's the kind of biggest departure that depends what you impose to be very, very easy to see. And in this case, it's the symmetry of this matrix.
Thanks.
All right, let's next take a question from Julio.
Hi, thanks for a very nice talk. So for non-integral theories or in higher dimensions, you should have particle production. Is there any conceptual obstruction to think?
No. So in 1+1d, you didn't need to use integrability to derive the thing. So it's the same. You can generalize it. Just the integrable case is nice because you have some closed formulas and you can test the prediction. No. So I don't think that's in higher dimension, like the biggest difficulty is that if you just do group-like symmetries, you don't learn anything new. It's just a thing-starting representation of groups, which you know very well. And these generalized symmetries act in nice ways, not on particles, but on extended objects. So for example, in 4D, you can think of a confining theory, and you have the confining string. And in that case, there is a nice non-trivial action. So then you have to look at scattering of strings, which is more complicated. So in higher dimension, and also the mathematical tools for the representation theory are not well developed, like in this case where it's kind of known what are the structures. So you have to, try and error a bit. And but it's, I think for some special cases, it's within reach. The hard thing is to understand the scattering of these extended objects, though. So the constraints are maybe easier to write, but understanding the dependence on momentum is hard. So I don't know how much you get, but yeah.
No more questions? Okay, all right. In that case, we can thank Christian again.